So today's speaker is Professor Frank Pollmann from Technical University of Munich. So he's actually giving this talk from Germany. So Frank got his PhD at the Max Planck Institute for Physics of Complex Systems. And after that, he was a postdoctoral fellow at UC Berkeley. He went back to Max Planck, and he was the group leader for some time. Then he moved to Munich to become a professor there. So Frank is very well known for his pioneering work, especially in making connection between quantum information science and quantum many-body theory. So he's basically a pioneer for that field. So this is relatively new and rapidly developing field, and Frank has been at the forefront. So I'm really glad that he agreed to give this talk today. So yeah, so with that, Frank, please go ahead.
Okay. Thanks, Youngbeck, for the introduction, and thank you for the invitation to give a colloquium here. Unfortunately, I couldn't make it to Toronto in person, but I hope to visit maybe some other day. So yeah, in the next 45 minutes or so, I want to discuss some ideas that are around now about how we can use quantum processors to study properties of quantum matter. And the background is that over the past couple of years, there have been quite important breakthroughs on the hardware. So in particular, now the first quantum computers are available to us that we can use for running simple programs, simple quantum programs. And the question that's in the room now is like, what could be one of the first problems which is really suitable to be attacked by a quantum computer? Right? Maybe going back in history, when the first computers came up, one was probably also wondering what is a problem really suitable for a quantum computer, because certain tasks that are very easy for us humans are very hard for computers. So we just needed to identify problems that are well suited for these computers. And one found, for example, one of the first algorithms used were Monte Carlo algorithms to study properties of materials. And now the question is like, what are good problems and what are the suitable algorithms for the first quantum computers? And then this is exactly what I want to talk about in the following. Let me start by giving a little bit the background. Right? So I want to discuss a little bit why we are interested in different phases of matter and what the type of phases of matter are that we find particularly interesting in modern condensed matter theory. So before getting there, let me start by giving an example that's well known to all of us, and this is here water, right? Water can appear in different phases, and here we see two of them. So we see the liquid phase of water, and we have the ice phase of water. And these two phases of water are distinct in terms of the symmetry properties. So in particular, the liquid water has the full continuous rotation and translation symmetry of space, and this symmetry is then spontaneously broken when the water freezes to ice. And based on these symmetry breaking, we understand the mechanical properties of ice, like the rigidity is due to the symmetry breaking. And also, thanks to Landau many years ago, we have a very powerful framework that allows us to understand the phase transitions between these phases. And what I'm here demonstrating along this nice picture of water and ice is an extremely powerful and general framework that allows us to understand phases in magnetic systems and nematic systems. So there are various systems to which these kind of framework can be applied, and allows us to distinguish and understand various phases of matter. Now, over the last couple of decades, it was found that there is a whole lot more than these phases that are, or that can be understood in terms of spontaneous symmetry breaking. And I'm not going to discuss this in a lot of detail, but I'm just showing two particularly nice examples. The first example I'm showing here is the fractional quantum Hall effect. And the fractional quantum Hall effect appears or occurs when we take a two-dimensional electron gas and apply a strong perpendicular magnetic field to this at sufficiently low temperatures. This is basically the setup, and what's happening in the system is that at certain magnetic field, it forms a rather exotic phase of matter. And what makes this phase of matter very distinct is that in this case, the electrons that actually form the electron gas, or that are inside of our sample, can fractionalize into new sort of collective excitations that only carry a fraction of the charge, right? At this magnetic field here is a magnetic field, and here is a so-called Hall conductivity. And at this plateau here, where we have this magnetic field strength, at this magnetic field, the electrons decay actually into fractional charges, each carrying a charge of E/3. And that is quite exciting, because we have now a case where the elementary excitations are now carrying fractions of the elementary charge. And moreover, and this is one thing that I'm going to comment on in a moment, is that these particles are even more exotic than carrying a fractional charge, because these particles are particles that are having an exchange statistics that is different from the bosons or fermions that we are used to, right? So we know that particles can be distinguished in terms of, or quantum particles can be distinguished in terms of bosons that, when exchanged, don't give any phase. If we just take a pair of fermions, we exchange them, the wave function picks up a -1. Turns out these anyons go beyond it, and we can, for example, have a case where if we exchange them, we just pick an arbitrary phase of phi, and this is why they're called anyons. So this is one example. Another example are certain materials that are currently kind of the attention of many experimental physicists, trying to identify materials that, when being cooled down to low temperatures, don't order in a conventional way, right? So recall, if we take a simple ferromagnet and we cool it down to low temperatures, the spins will just order, for example, ferromagnetically or antiferromagnetically. There is, at least on the theory side, many systems that have been predicted that at lowest temperatures, they would not form any ordered state, but instead form a so-called spin liquid, which exhibits properties which are very similar to the one of the fractional quantum Hall effect. For example, we can have a fractionalization of the spin excitations. So if we just create a magnon excitation, for example, this magnon can decay into so-called spinon excitations, and they might again have these exotic properties. So the main point I want to make is that if we take a certain class of materials or of systems, we cool them down to low temperatures, that the interplay of quantum mechanical fluctuations and the interaction between these simple constituents can yield rather exotic and exciting physics. And as a condensed matter theorist or physicist, we are actually in a pretty great position, because we actually do know all the underlying or the relevant equations. So we know that whatever material we want to describe, it is described by the kinetic energy of the nuclei, the kinetic energy of the electrons, the interaction between the electron among each other, the interaction among the nuclei, and the interactions between the electrons and the nuclei. So we know how to write down very general equations that, when solving them, would actually tell us if a certain material would become a spin liquid, or if it would form maybe a ferromagnet, or if another material would become a superconductor. So all these informations are contained in this information. The only problem, and that's a big problem, is that solving these equations is incredibly hard. Solving these equations classically would already be hard, but quantum mechanically, it's even more difficult. And what we often do is that we just simplify the model to a lot. So let us say that we start from this very general expression that I just showed a moment ago. But if we say want to understand a spin liquid, maybe it's already sufficient to consider a system where the spins of the electrons are just localized. So we don't need to consider the motion of the electrons. We can assume a certain lattice structure that has formed. So we can make a number of well-justified approximations and eventually boil it down to a seemingly simple model. So we could, for example, just say that, well, we identified the lattice structure, which could be, for example, just a simple Kagome lattice. So this is the lattice that is shown here. And let us now assume that the degrees of freedom that we are considering are simple spin 1/2s, which have a two-dimensional local Hilbert space, so they can maybe only point up or down. So now there's a step where we would have simplified the problem already a lot. But then we are left with a Hamiltonian to which we have to find the ground state, right? So we came from this very general equation, we just removed degrees of freedom, so we just performed several approximations to eventually have a Hamiltonian that lives on a much smaller Hilbert space, for example, just the one of spin degrees of freedom on a lattice. And now we have to solve this problem, and that means what we have to do is we have to find the ground state for a Hamiltonian. One way of solving it is to just take the Hamiltonian and solve it on a computer. And the problem is that we are now dealing, or the problem, if you want to understand quantum mechanical properties of these systems, we have to solve a quantum many-body problem. And this means that the equations that we have to solve live in an exponentially large Hilbert space. So if we, for example, take n of those simple spin 1/2 degrees of freedom, we have to diagonalize or find the ground state or find the lowest energy eigenvalue of a matrix that has a dimension of 2 to the n. And now we can ask, like, using the algorithms available to us for a generic problem, how many of these very simple quantum particles can we actually simulate on a state-of-the-art computer? And here's a picture of the supercomputer that we have here in Munich. And sadly, even the largest computers available to us, and using the most efficient algorithms that we have, we can only simulate the order of 40 or so of these simplest quantum particles, right? So here I'm just using qubits for putting it into the context of quantum computers, but this is the same thing. So the simplest quantum particle, which has only 2 degrees of freedom of pointing up or down, corresponds exactly to the degrees of freedom that a single qubit has. So using state-of-the-art classical computers, we can simulate about 40 or so qubits. That's in many cases not enough, because many of the questions we might want to answer, for example, what is the ground state of a spin system on this Kagome lattice, requires knowledge of way more than 40 qubits. So this is where we are now, we as a community are excited about the advent of the first quantum computers, because already the first quantum computers available to us have the order of about 50 or so qubits right now, and the number of qubits is increasing somewhat fast. And looking at the roadmap of IBM and Google, you actually see that they are planning to have the order of 1,000 or so qubit in the next couple of years, and that would be amazing. And it's particularly amazing, keeping in mind again the exponential growth that I mentioned, because if we want to use a classical computer to simulate not 40 but 50 qubits, there would be a factor of 1,000 in between, right? So going from 40 to 50, there would be a factor of 1,000. So we see that these are already simulating this model would be practically impossible on current computers. That, however, draws a bit of an idealized scenario, because these 50 qubits that are available to us on nowadays, like on the current quantum computers, they are far from being perfect. Meaning that if we have a computer, we are used to these computers being pretty perfect. So if we write a computer program, it can be as long as we like to. The computer program is on the way, not forgetting how it started. And this is still the case for these quantum computers, because these quantum computers that we have access to nowadays, they don't have error correction. So we are losing information if the program is getting too long. And still there are many questions about the scalability, how good the each gates or how the operations can be implemented, how long can the programs actually be. So there are many open questions on the hardware side. But at this moment, we find it actually interesting to now identify problems that are expected to be hard on classical computers, but doable on near-term NISQ devices. And NISQ stands here for the near-term kind of noisy intermediate scale quantum devices. Right? So these are, when I'm referring to NISQ, what I mean is that these are quantum computers that do not have error corrections and that have noisy qubits. And the task is now similar to what I mentioned before, where we have now a new device and we still have to figure out how to use it in a smart way. Because we can certainly come up with several problems that might be as hard on quantum computers as they are on classical computers. But here we are quite hopeful that problems in condensed matter or are a quite suitable type of problem, because here we just really one-to-one can think about how to map a quantum state that we expect, like for example, that we can just map the ground state of a specific problem that we are interested in into a program on a quantum computer. Right? So it's these kind of problems are not very far away from each other. Before discussing exactly this part, before discussing some ideas about how we can use quantum computers for simulating quantum matter, I want to just contrast classical computers and quantum computers just using a similar language, because computers or classical computers are all around us. We might just have a different view on them, but here I'm just trying to give a very schematic view on how a classical computer works. So we can prepare an input state, and the input state consists of bits. So I can here on the left-hand side, I can now start from a bit string, so maybe 0, 0, 1, 1, representing, for example, a decimal number. And now I can choose a set of gates, and here I'm using this called not AND gates, which are known to be a universal set of gates, meaning like every classical operation, every classical computation can be expressed in terms of a sequence of these gates. And eventually I can just read out something, and this could be, say, 0 or 1, depending on whether the input was a prime number or not, right? So I can now come up with a certain task and now find a gate sequence that solves this task, and then I can just read out a bit here or a bit string that is a solution to my problem. And this is what a computer is doing 1 million times a second. Now let's contrast this to a quantum computer. In the quantum computer, a quantum computer operates now with qubits. So each of those inputs here, each of those is now not a bit, which is either 0 or 1, but it is a qubit, which can be in a superposition. Like basically all these states together form now described by a quantum mechanical wave function, which can be in all sorts of superposition of all of those states, meaning using the numbers that I had before. So if we have now n qubits, we can now have 2 to the power of n different bit strings. And during the operation that a quantum computer does, it can form a superposition of all of those 2 to the n bit strings. And as we have a classical universal computer given by just having these NAND gates, we can again come up with a gate set for a quantum computer, which consists of different unitary operations, so-called Hadamard gate, C0 gates, and spin rotations, that then allow us to perform any possible unitary operation on these states. And by this, we can now perform every quantum operation on these qubits, and by this perform quantum computations, and eventually we can perform some measurement on some or all of these qubits. Right. So these diagrams are not directly contrasting classical computers acting on bits, having a universal set of gates, and then we can just read out a bit string. And for the quantum computer, we have now qubits as an input. We have now a universal set of so-called unitary operations that, in the meantime, form superpositions of all those 2 to the n bit strings, and then we can perform measurements on these. And now we want to use exactly this kind of setup to solve problems relevant in condensed matter physics. So now I want to discuss 2 concrete examples related to these rather exotic quantum phases of matter, right? So I pointed out that there are quantum phases of matter which cannot be characterized by symmetry breaking, but instead have some other rather exotic properties. And here I want to think about how we can now use quantum computers to study these phases and their phase transitions. So, and what I'm going to do first, I want to give a little bit of background to the physics of these phases of matter and how we can understand them theoretically, and then demonstrate how we can study these properties using quantum computers, and actually going to show how we can actually run these ideas on actual hardware. So the starting point is now the so-called cluster state model, which is a simple one-dimensional spin chain. So we take now these simple, like these simplified spin degrees of freedom that can only point upwards or downwards, and we have now a Hamiltonian for the describing the interactions between these spin degrees of freedom. So the second term is the easier one. So this is simply a magnetic field in x direction acting on the spins. This is a very simple term, and we all know that the ground state of this term would be just a state where all the spins are aligned in the x direction. Right? So here we have a very simple ground state. The other term is a bit more involved. It's a term where we have now the product of three spin matrices on neighboring sides, so sigma z, sigma x, sigma z. However, for this term, we can again simply find the ground state, and the ground state is a so-called cluster state, which I'm not describing in a lot of detail. But the main thing I want to stress is that this model has a certain spin rotation symmetry. And if we just look at the case where G is equals to 0, it has a ground state that is symmetric with respect to this Z2 cross Z2 symmetry. And if I make G very large, it is also, the ground state is also symmetric with respect to this Z2 cross Z2 symmetry. So that's now interesting, because using this simple framework of Landau, or like the simple classification of phases in terms of spontaneous symmetry breaking, we would actually expect that these might be the same phase because there's the same symmetry. However, if we now in this simple model tune this parameter G, we observe that there is a phase transition in between. So there's a phase transition where the gap closes and we have a diverging correlation length. So we have now a phase transition between two symmetric phases. And turns out we can understand this in terms of so-called symmetry fractionalization. This is telling us basically how the symmetry is represented in terms of the edge degrees of freedom of a finite chain. I'm not discussing this in detail, but there is a mathematical framework that actually distinguishes the left phase from the right phase. And there's a direct consequence, and the direct consequence of the different ways how the symmetry acts on open chains, or like the ends of a chain, is the existence of a so-called non-local or string order parameter. Right? So this is now quite interesting, because if we have just a simple transition between a paramagnet and a simple ferromagnet, we can use a local order parameter, meaning we can just measure the magnetization, and the magnetization allows us to distinguish the ferromagnetic from the paramagnetic phase. Here, we don't break any symmetry, and thus we cannot have any local order parameter. However, we have what we call a non-local order parameter. We have now a string of operators which has to be very long, and take the expectation value of this, and we can show that this has to be 0 on one end of this transition, and it can be non-zero on the other side of this transition. So to recap, so what we have here is we have now found, identified a simple model that exhibits a phase transition between two symmetric phases, which can be distinguished in terms of these non-local order parameter. So, and this is why we call it a topological phase. Now let's come to the study of this using a quantum computer, right? So because now we have this somewhat exotic phase transition between two symmetric phases, and I want to demonstrate how we can now use these a simple program on a quantum computer to study it. And for this, at first glance, I want to make this model a bit more complicated, which helps to make it simpler. So let me just help to understand this triangle that I drew here. So if we look at the bottom part of this triangle, this is exactly the line that I showed on the slide before, where we have now on the left-hand side just the cluster state. On the right-hand side, we have just a simple paramagnet. And along this line, we have now a phase transition. And now I add another axis to it by having a simple ferromagnet. So this is just an Ising ferromagnet. And if we go on this side of this triangle, we actually have now a transition between the cluster state, which is symmetric, to a symmetry broken Ising model. And on the other side of the triangle, we have here now a transition from a paramagnet to the Ising ferromagnet. So here, this is a simple Ising transition that many of us might know. But now it turns out that if we take the parameter space as shown here for this somewhat generalized model, I just show here this black parabola. And it turns out if we move along this black parabola, the ground state has an extremely simple form. So in particular, we can just represent the ground state in terms of a sequential application of these gates. And this is now quite nice, because if we stay along this black line that actually crosses from one phase to the other phase, we actually can write down a very simple program that, after running this program, it creates the ground state of this Hamiltonian. And this is now very useful because we don't have to perform a variational optimization of the energy, or we don't have to run complicated operations. All we have to do is we just run this sequence on of a few gates on a quantum computer, and we obtain the ground state for this Hamiltonian, and then we can perform measurements on this state that we created to diagnose, for example, the phase transition or different order parameters. And this is exactly what we did. So we used, in this case, a 20 qubit IBM quantum computer. We run the program. So we run this program which creates now the ground state of this Hamiltonian along this path. And then we can measure the string order parameter. And without going into a lot of detail, we are using interferometry to do this measurement, which turned out to be very useful. So in particular, we just have now some extra qubit that we use on this computer. And we are then using this Hadamard gate. And this Hadamard gate, it just creates a state which is now 0 plus 1. So it just creates a superposition state of up plus down. And then we just apply a so-called controlled operation. So we have here now the superposition of up plus down, and then on the channel where the spin is up, we apply the string order. Where this spin is down or 0, we do not apply the string order. And then by measuring just a single qubit, we can by this measure the expectation value of the string order parameter. So this is a very useful trick for doing these measurements on the quantum computer. And here, this plot is now showing the result from the actual device. And we see that as we tune now the parameter G, we can now measure the value of the string order parameter. The black line is the theoretically expected value. And we see that indeed the measurement nicely distinguishes the two phases, right? So we just actually cross the phase transition, and the string order parameter can measure it. So the nice thing here is that because we can now write this in a fairly short program. It can actually be represented on a real machine. But what we also see is that there is still a significant error compared to the exact result. And this is due to imperfections in the machine. So the gates are not implemented correctly. And also as we do these operations, the system couples to the environment. So there are lots of errors included. So we see here that even for this fairly simple program, there's a significant error. But this can in principle be generalized to like these kind of idea of coding the ground state can be generalized to a very large class of different topological phases. Good. So this was the first example that I wanted to demonstrate, where basically we managed to come up with a simple short circuit that allows us to program the ground state of a Hamiltonian crossing a phase transition in this one-dimensional model. Now, let me then change gears and discuss now another example. And this is an example where we consider a different type of quantum matter, the so-called toric code phase, which is a so-called topologically ordered state on a quantum computer. So similar to what I discussed before, I want to just show you a simple toy model that does realize the phase. And this is the so-called toric code model. Right? So now we just go up one dimension. So we have now a two-dimensional lattice. So we just take the square lattice as shown here. And the right, so there is a question in the chat. I just see things. So there's a question saying that the Hamiltonian has a three-body term, yet the unitary gates in the circuit span only 2 qubits. Yes, so this is right. So the Hamiltonian has these three-side terms, and to construct the ground state, we have now a sequence of these two-side gates. And there's no contradiction, because having this sequential application of these gates can create correlations between all those spins. So we can really just create a large number of different states. So if you just, instead of having a program for a specific state, if you want to see this as a variational manifold, you can actually create many possible states using these kind of sequential application of these gates. The form how you can create each of those is just some C0 and single qubit rotations. So each of those can be expressed fairly simply using elementary gates that are implemented on, for example, the IBM quantum computer. I hope this answers your questions. Thanks. Good. So let me now move up one dimension and now look at a different type of topological phase as compared to the one we discussed a moment ago. And this is at least in certain communities, well-known toric code model. And the toric code model itself actually had been proposed in the context of so-called topological quantum computing. So, but that set aside, so the model is now the following. So we just take a square lattice as shown here, where we have now spins living on the edges of the lattice. So all these black dots correspond to spin degrees of freedom. And the interaction is now a 4-spin interaction. So we have this vertex term, which is now a product of sigma z's. So we have a sigma z product on all of those 4. And we have the red ones, which are the plaquette terms, with the product of sigma x's. After doing some algebra, you find that it's actually an exactly solvable model. And the ground state of this model consists of an equal weighted superposition of all of those possible loop coverings. And the loops are now drawn by saying that whenever you have a spin up, you don't do nothing. And if there is a spin down, you just draw a loop segment. And then you find that the ground states can be represented just by this superposition of all possible loop coverings that you can draw on a lattice. And this type of state has now some what is called a Z2 topological order. Right? So this state has now this particular type of topological order. And in fact, similar to the wave function that I advertised before, realized in the fractional quantum Hall effect, this state gives rise to these anyonic excitations. It has these kind of rather exotic particles that are neither bosons nor fermions. So in a spirit similar to what I discussed before, we can now construct a circuit, or we can construct a program that we can code on a quantum computer that creates exactly the ground state of the toric code model. So, and this is now illustrated here. So just to help you to orient yourself, so the black lines are the same black lines on the previous slide, where we have the qubits, or the spin 1/2s, living on the edges. And now we just apply a sequence of gates. So we apply Hadamard gates to a subset of those spins. We apply then, starting from the center row, center column, sequences of these C0 gates, indicated by these guys here, to the lattice, and pull this through. And after pulling it from the center to the outside, we actually then create a state which is exactly this ground state of this toric code model. This is exactly now the superposition of all loop coverings of the lattice. And the way that we can test that this is actually the state is we can measure now the plaquette and the vertex operators, and if they are -1 on each of the, or if the expectation values of this operator and this operator, they are both 1 on the stars and the plaquettes, then we are in a proper ground state. So this is actually how we can now test whether the mission of getting the ground state was successful. And this we've done, and what you're looking at now is data from the Google quantum computer. We see that indeed the fidelity of the state is at about 90%, right? So running this program, we actually get the toric code ground state with a very high fidelity. So that's good news. So we have a fairly simple code, the order of several tenths of gates, that we can apply to create then the ground state of that model with a very high fidelity. So now we can, similar to what we did in the case before, think about how can we characterize the state. So we can now use this as a test case to study characteristic properties of these phases of matter. And as I pointed out, that the characteristic of this kind of phase of matter is the existence of these exotic particles, and in hand goes with this so-called topological entanglement entropy. So it would take a bit too long to explain in detail what this is, but the entanglement entropy is now a measure that measures the entanglement between different partitions. So we can just look at the degrees of freedom that are, for example, inside of the circle, and the entanglement entropy would in this case measure the amount of entanglement of the degrees of freedom inside and outside. And there are some corrections gamma. And the main point I want to make is that this, if we can measure this correction gamma, that gives us insights into the phase. So that serves as a non-local order parameter of this kind of phase. And moreover, what we could test, we could directly test the exotic properties of those excitations. And indeed, now using the framework that we have, we can now determine exactly these quantities. So we just create the state, and now we can do measurements on the state. And this is a busy slide, but all that you have to look at is basically this panel here, because here what you see is that for different partitions, different positions on the chip, we see that it always peaks here around square root of it peaks here around the logarithm log 2, and this is exactly the theoretically expected value. So these measurements show that the ground state created by this program actually contains this non-local entanglement as predicted by the topological theory describing this kind of state. And the other property I mentioned is that these kind of states give rise to rather exotic excitations that we don't know from our everyday life, namely that we can have particles that when being exchanged are neither bosons nor fermions. And this again we can measure directly, so we can now take the ground state and now we just apply a sequence of these gates to move around those excitations, and we can now emulate the braiding or the exchange of these particles directly on the chip. And the way that we measure it is again using this method of interferometry, similar to the one used for measuring these string order parameter. In particular, we just now create two copies of a system where we have an extra qubit pointing up or down, and then we just can measure the interference between the two paths, where we just in one do an exchange and the other one we do not do the exchange, and then we can do the measurements. And again, from the theory, we know exactly what to expect. So we know exactly what are the phases that we get for exchanging different particles. So for example, if we just take a so-called magnetic excitation that we have in these systems, we take two and exchange them, we get a phase of 0, and the result is really near 0. If, however, we are exchanging a bound state, like a molecule of an electric and a magnetic particle together, and we exchange them, they form emergent fermions again, and we should have a phase of pi, and this is where the result is pretty close to, right? So we see that not only can we generate the ground state of this model, but we can also emulate or simulate the braiding of these exotic excitations directly on the chip. And lastly, and I'm just going to mention this, that as I pointed out, the toric code had originally been proposed as a very robust memory, because memory, like the quantum information, can be stored in a rather non-local way. And changing the boundary conditions of our system, we can now simulate it, and indeed we find that we can have a rather robust representation of qubits. So let me now conclude. So what I wanted to discuss is basically how we can use sort of near-term and current quantum devices for studying questions that are relevant for understanding quantum matter. The concrete examples that I discussed is one. First, I showed how we can simulate on a quantum computer the phase transition between different symmetry protected topological phases. And the second part, I demonstrated how we can analyze certain properties or characteristic properties of topologically ordered states on a quantum processor. And let me state, at this moment, we haven't done anything that we could not do on classical computers. But the hope is that if the devices scale up and if they scale as promised, this will be a route where we, in the pretty near future, would be able to actually have results that would be hard to actually get on classical computers. But that depends really now on how fast the developments will be on the hardware side. So with this, I want to thank you for your attention, and also my collaborators. So together with Leo, who's a student in my group, and Adam, who was postdoc, and my colleague Michael Knapp, and colleagues from Microsoft and Google, we did the experiments on the toric code. And together with Andrew Green and my current PhD student, Bernard Jobst, we looked at the SPT phases. So